In the last video, I left you off with this term, and this term was called transmetalation. So we want to talk about what transmetalation actually means. What is it? Why is it important? Why should we worry with it? And we're doing it very early on because we've already talked about this idea that there are plenty of metals that can take place in organometallic. And we've already talked about two of them, lithium, magnesium. And we've talked about how to form these and how to make these so that way we can use these, create these negative carbons that can then turn around and react with other reagents. So transmetalation is discussed very early on because trans means change. So transmetalation means changing metals. Huh? What does it mean? Well, let's say that we've got an organic, and off of this organic, we have a lithium compound. And let's say in solution, we also have little innocent magnesium. And I'm choosing these two metals because these two metals are the two metals that we've talked about so far. But keep in mind that any metal is fair game. Okay, so I've got this organic. This organic is involved in a bond. So here's carbon, and that's bonded to lithium, and they're in a relationship together. There's a bond there. And carbon and lithium has electronegativity values, and carbon has a higher electronegativity value than lithium. So this is why carbon sucks all of the electrons up toward it, and lithium is very exposed, and I get a partial positive. We see this teeter-totter relationship goes back and forth, and carbon sucks and sucks and sucks and sucks and takes every dollar and cent that lithium makes, and lithium cannot put up a fight. And imagine you in a relationship that way. You and carbon are in a relationship, and carbon wants and wants and wants and wants, and you provide and you provide and you give everything that you have until you can't give any more. Can you imagine the arguments that go on there? The same thing happens with carbon and lithium. There's arguments that are involved here. Yeah, carbon gets what it wants for now, but this relationship is a very toxic relationship. Okay? It's just like real life. You can imagine a scenario where lithium's going to come in one day after work and say, "Carbon, I've had it. I've had it. No more. You're not going to keep taking everything that I make, everything that I bring to the table. Something's got to give." I'll tell you what's going to give. Carbon and lithium is going to argue so much about this pitter-patter of electrons back and forth that carbon, one day while lithium's gone to work, will look over at this magnesium and go, hey, lithium's went off to work already. Lithium and we just argue all the time. It's all about money every single time. It's all these fiscal problems with these electrons. So magnesium, why not come around a little bit? We'll see if we can get along. We might form a better bond. So that's kind of what happens here as far as these organic reactions go. Well, what does that really mean? So here we have an organic, and then there's a carbon. Off of this carbon, I have a lithium, and then maybe, just maybe, a magnesium now has come into the picture. Hey, do you know what carbon's doing while you're at work? I mean, you call carbon up at lunchtime and you're like, "Hey, carbon, what's going on?" And they sound real sneaky. Well, that's probably because that carbon's out seeing magnesium. So what happens here is that carbon looks at the electronegativity value of lithium, and it looks at the electronegativity value of magnesium. All right, well, what are those values? Well, let me pull up that chart and I'll show you what those values are. So if we look at lithium, we've a 1.0. Magnesium is a 1.2. So there's a difference here. All right, so this is what this means. Carbon and lithium can be in a relationship. And carbon is stronger than lithium as far as electronegativity goes. Carbon's 2.5. Well, carbon and magnesium can also be in a relationship. And magnesium has a little bit higher electronegativity value, which means that carbon is a little bit weaker. It can't have its way like it can have its way with lithium. You know, carbon's still going to get what it wants. Don't get me wrong, carbon still gets what it wants. 2.5 versus 1.2. But magnesium is going to put up a little bit more fight, meaning that when it comes home and carbon's like, could you give me $20? Magnesium's going to look and say, no, you should make your own $20. I'm not giving you $20 today. Sorry, it's not going to happen. You need to go out and get to work on your own. Make your own money. So carbon and magnesium, in that sense, they're more equal. And because they're more equal, it brings a little bit of stability to that relationship. Carbon and lithium fight all the time. Carbon and lithium have this bigger electronegativity difference. And because they fight over and over, it makes that relationship very unstable. Carbon and magnesium, though, carbon still kind of calls the shots. But carbon and magnesium, they don't get into as many fights as carbon and lithium does. And that's because their electronegativity is a little bit closer than that of lithium. And because it's a little bit closer, magnesium's going to stand up for itself a little bit more. Magnesium's going to say no sometimes, not all the time, just sometimes. And that prevents the arguments from happening. It prevents magnesium or lithium to feel down and out about themselves. So here's the story with this concept. If I have carbon, and carbon has a choice between two metals, let's say it's currently bonded to lithium, and magnesium comes in. Carbon's going to question this. And it's going to go, which one is going to be better for me? I'm looking long term. Lithium has an electronegativity of a 1. Magnesium has an electronegativity of 1.2. Carbon has an electronegativity of 2.5. Because magnesium is a little bit closer to carbon, carbon's going to say, hey, magnesium, I think that we're going to hook up together. And I think that we're going to do this, and the reason for this is because our electronegativities are a little bit closer. I know that I can't get my way every single time. I'm still going to get my way, though, the majority of the time. But we're not going to argue as much. And this is going to be a more stable, non-polar bond that happens between the two in comparison to the carbon-lithium bond. All right, so what I mean by that is carbon-magnesium will still have a charge distribution. It still will be there, just like carbon and lithium will be there. But out of these two choices, carbon and magnesium has a lower difference in electronegativity value. Because of that, they are regarded as more equal to each other. And because of that, they create a more stable bond between each other. They are not as polar as carbon and lithium would be, and they stay around a little bit longer. And that is how transmetallation happens. So transmetallation, carbon maybe could have a relationship with lithium. We throw magnesium into the picture. Carbon says, lithium, you got to go because I found a new man or woman in magnesium. And now lithium will go off into the sunset, crying and boo-hooing, hoping to find another relationship somewhere later down the road. Trans means change. Metallation is metal. We have changed the metals on the carbon. So if we have a lithiated carbon, we can convert that to a magnesium carbon through the process of transmetalation. And this is really all that it takes. It just simply takes the presence of one metal over the other. And folks, that's it. That's all there is to transmetalation. It's all about the electronegativity differences. So if I go back to this chart and we take a look again at this chart, and let me get rid of all of this garbage off of this chart. It's starting to, look messy and nasty, and it's starting to aggravate me. So let's get rid of that. Again, we're looking at carbon. And let's say that it has a choice between cadmium and maybe calcium. I don't know. Let's say that that metal could be used. Well, we're not going to see calcium that much. So let's say cadmium and copper. Which one would carbon prefer? Which out of the two metals would carbon prefer to be hooked up with to create, here's the thing, to create a more stable organometallic? Well, I'll look at copper of 1.8. I'll look at cadmium at 1.5. So it looks to me like carbon at 2.5 and copper at 1.8, they're a little bit closer together than 2.5 and 1.5. Take the difference between the two. Copper is a little bit closer to carbon. These electronegativity values are closer, which means this is more of a nonpolar compound. It's still polar, but it's more of a nonpolar compound versus the other option of cadmium. And because they're a little bit more equal to each other, it increases the stability when they come together. And if it increases the stability, then it's going to last longer. So if carbon had a bond to cadmium and we throw copper into the mix, that carbon could undergo the process of transmetallation. It could decide to kick cadmium off and pair up with the copper instead, because that copper bond now is going to increase the stability of that compound to the metal. And it's all about electronegativity. That's what it's all about, folks. That's what it's always been about. Ever since day one, it's what it's always been about. And that's how we describe, and that's how we think of transmetallation. So in this next video, we are going to go on to another metal, another common metal that is in the world of organometallics. So we've got this concept now of what an organometallic actually is. We have some type of metal on an organic. We've talked about two, lithium and magnesium. We now know that carbon prefers metals if I'm giving carbon a choice on which metal to choose from. And sometimes we're not going to give it the choice. That way it can just deal with the metal that's given to it, and that's it. I mean, that's life sometimes, right? It's the hand that you're dealt. But in this next section, we're going to focus on something called the Organocuprate family. All right, well, I hope that you know what cuprate means. Cuprate refers to cuprous and cupric. And if you've taken general chemistry, and I know that you've had because you've made it to Orgo 2, then I hope that you know what cuprous and cupric mean. And this is referring to copper. That's where the elemental symbol Cu comes from. Copper is C-O-P-P-E-R. There's not a U in sight. Why do we give it a Cu symbol? That's because it comes from the old school name of cupric and cuprous. So organocuprates will be on the table next. So we need to kind of do the same thing that we did with lithium and magnesium. We need to talk about these cuprates. We need to figure out maybe how they're made. Do they go by different names? What type of solvents do they prefer? And then how do they react? We've already discussed how lithium and magnesium reacts. We know that they create negative carbons. So do the coppers do anything different? I mean, if so, maybe that's why they put them in their own category. But if so, what is it that they do different? What are the things that I need to watch out for? So folks, that's what we're going to do in our next video together. We're going to focus on organocuprates, and we will go from here. So until then, sayonara, come back and see me, and when you come back, maybe bring me some popcorn or something to drink. I'll be here waiting.